Hello everyone, welcome back to my channel. My name is Dr. Yogita Bisht and in today's video we will talk about the Pauli Exclusion Principle. So just a quick reminder, this is the third video of my video series Electronic Configuration. In the first part we studied about the basics of the quantum number and in the second part we studied about the Aufbau principle and today we will talk about the Pauli Exclusion Principle. So these videos are very important to understand the complete electronic configuration. So if you have not watched those videos, I would suggest that you should watch them and I will provide the link for them as well. Alright, so let's just begin with the Pauli exclusion principle. So before that, if you can recall, I told you that the quantum number are basically the address of any electron in any atom. Okay, now what does this Pauli exclusion principle says? It says that, just a second, that no two electron of an atom can have same set of 4 quantum number. Okay, so let's just try to understand it in a little bit of layman language. Consider two persons, A and B. They both live in the same country. Let's say they both live in Germany. Okay, and then again they stay in the same state, let's say Berlin. And further, if we move further, let's say they also live in the same street. Let's say Antonstrasse. So we have 4 quantum number, right? So as per this rule, they are saying that Pauli exclusion principle says that they can have the same 3 quantum number. It is possible 2 electron of same atom. They may have the same set of 3 quantum number, but the fourth one need to be different. Okay, that means if they are living in the same country, same state, same street, still they need to be live in different building, or maybe if they are living in the same building they need to have different apartments. All right, so let's say its house number is 8, its house number should be 10. Okay, so this is the simplest example to understand this rule. Okay, so if you try to understand this in terms of chemistry, consider, let's say, carbon. Okay, so its number of electrons of carbon are 6. So if we write the electronic configuration, it need to be 1s2, 2s2, 2p2, right? If you can recall, these are the energy level we studied in the Aufbau principle, and as per the Aufbau principle we need to fill the electron as per their increasing order of energy. So 1s has the lowest energy, that is why first 2 electron will be filled here, the next 2 in the 2s and next 2 in the 2p orbital, right? So if we represent it properly, we can also represent it like this. Okay, so if you are wondering why S has a single orbital and P has 3, then you can go through my first video of this video series of the quantum number. You will understand everything. All right, so if we start filling the electrons, we fill electron like this. Okay, because we need to fill 1 electron in each or 2 electron in each. So this is 1s2, this is 2s2 and this is 2p2. Okay, so if we try to understand the quantum number of each electron, these are the each electron and each one of these electron have different address. So if I talk about this particular electron, so here the principal quantum number, as you can see, is 1 for this. And what about the azimuthal quantum number? Since it is S, so for S, azimuthal quantum number value is 0. For P it is 1, for D it is 2, and so if you can recall this. And then for angular quantum number, this is, here the angular quantum number is also 0, and the spin quantum number in this particular case, since we have up spin, it will be plus half. Whereas if we start writing the 4 quantum number for this particular electron, in this case again n is 1, L is 0, ml is 0, but ms in this case would be minus half. So you can see that both the electron have different set of 4 quantum number. Even though first three were same, but in this case the last one was different. Same goes for this electron. We can write all the 4 quantum number for this electron also, right? So in this case, for this particular electron, if you want to write, it will be n is equals to 2, right? Here L is again, for this is s orbital, L is 0, ml is also 0, and ms would be plus half, right? For this particular electron, n will be 2, L will be 0, ml will be 0, and ms would be minus half, right? So this electron has different address, this has different address, this one has different address, this one also has a different address. Now you can also write for this one as well, 2p1. So this would be n is 2, L for p orbital, L is 1, ml is, in this case, this ml value can have a, for 2p, it can have a value of -1, 0, and +1. So in this case, it has a -1 value. And ms, as you can see, it is up spin, it will have plus half, right? What about this one? So in this case, n is 2, L is 1, ml in this particular case, for this one, it will be 0, and ms again you can see plus half, because we have the up spin, right? So you can easily see that since carbon has 6 electron, all 6 electron have different set of 4 quantum number. Okay, this is what the Pauli exclusion principle says in a particular case of atom. So if we talk about the nitrogen, you cannot compare the electron of carbon with the nitrogen. Okay, you have, this rule is about the 2 different electron of same atom. All right. So from this, we can also conclude another point, which is also another statement of the Pauli exclusion principle. If you are talking about exam and somebody asks you to write the Pauli exclusion principle, you are supposed to write not only this statement, but you are supposed to write the other statement that says that, from this you can easily see that if I write up spin for this electron as well, that means this will be the violation of the Pauli exclusion principle. In that case, this would also become plus half, right? If I write it as a up spin, so that will be the violation of the Pauli exclusion principle. For example, if instead of 2 electron, if I fill another half electron here with a positive up spin, then again there will be violation of the Pauli exclusion principle. So from this we can also conclude one thing, that in a single orbital we can have maximum 2 electron. Here 2 electron, here also 2 electron. In individual 2p orbital also we can have maximum 2 electron each. So that is the another, you can say, the conclusion of the Pauli exclusion principle. It says only 2 electrons may exist in the same orbital, and these electrons must have opposite spin. As you can see, they have the opposite spin. This also has opposite spin. And if you study the further electronic configuration where we have more electron rather than carbon, maybe oxygen or some other electron, then for the further filling we need to fill other electron in the opposite spin. This is the another statement of the Pauli exclusion principle. Then we have one more statement, kind of sub-statement of the Pauli exclusion principle, which says the maximum number of electrons in the shell with principal quantum number n is equal to 2n square. This is another substatement of the Pauli exclusion principle, and we can prove that also. Okay, let's just say we start with n1 and then n2 and then n3. So as per this rule, the maximum number of electron for this particular shell, this shell is called as K shell, this is L shell, this is M shell. According to this rule, this K shell should have a maximum number of electron as 2. This should have a maximum number of electron 8, and this should have a maximum number of electron 18. So we just have to prove that. Okay, so let's just start. For n is equals to 1, we know that L can have a maximum value of 0, right? That is s orbital, right? So maximum number of electron that can be present in n orbital is 1s, and that maximum number of electron as per the Pauli exclusion principle that can come in this particular orbital is 2. So number of electrons are 2, right? In this particular case, possibility of L is 0 and 1. If you can recall, L is given by 0, 1 till n minus 1, right? So let me just erase this to avoid any confusion. So this was just a short recap of the rule. If you want to study it in detail, you can watch the previous videos. All right. So that means the possibilities are 2s and 2p, right? So in 2s we can have maximum 2 electron. What about the 2p? 2p has 3 orbital, and in each orbital we can have maximum 2 electron. So total number of electron at p orbital can held is 6, right? So in s we can have maximum 2 electron, in p we can have maximum 6 electrons. So that is 2 plus 6, 8 electron, right? Then what about the n shell? That is the n principal quantum number. So in that case, possible L values are 0, 1 and 2, right? So the possibilities are 3s2, 3p and 3d, right? So 3s can have maximum 2 electron, 3p can have maximum 6 electrons, right? And 3d, the number of orbital for d is 5, right? So maximum number of electron that it can held is 10, right? So it can have maximum 10 electrons. So 2 plus 6 plus 10, 18, right? So this is how we can verify also this rule. So just a short recap. As per the Pauli exclusion principle, no two electron of same atom can have same set of 4 quantum number that we proved with the help of carbon. Then it also says that in particular orbital, maximum number of electron that can present is 2, and both should have a opposite spin. And another statement says that the maximum number of electron which are present in a particular shell, that is K shell, L shell, M shell, is given by 2n square, where n represent the number of shell, the principal quantum number, right? All right then. So that is it for today's video. In the next video, we will talk about the Hund's rule, and finally we will study the more electronic configuration. All right. Thank you.